Now, good evening to you all. Actually, I was discussing the radio, radio physics for the PGTs of the radiology, and those who are preparing for their exam in the either in the first year or second year or final year in the Department of Radiology. Now, I am actually giving the videos of now various subjects, but in radiology I am strictly now focusing on the radiophysics, because after completion then I will go to the systemic part. Now, as I was discussing about the completed about radioactivity series, then I had to start about the radioactive equilibrium. Now, actually what we meant by radioactive equilibrium is that the radioactive equilibrium exists when radioactive nuclide is decaying at the same rate at which it is produced. The time and the decaying rate, when it is same and it is matches, it is known as radioactive equilibrium, and the disintegrating nuclear is known as parent, and the nucleus remaining after the event is known as daughter. So this is a very important concept about radioactive equilibrium, and daughter nucleus can be stable or radioactive and decays into another daughter and so on. Thus a series of decay arises with its own characteristic decay constant. So, and if the half-life of the parent is longer than daughter, an equilibrium may arise known as the radioactive equilibrium. Now, radioactive equilibrium is not happening immediately. Always remember that radioactive equilibrium is not happening immediately. Only after a transition period. This period may be in the order of the few half-life. Concentration of the daughter nuclei in the radioactive equilibrium depends on the proportion of the half-life of the parent or daughter. Now, the ratio of the daughter activity to parent activity, always remember there is a ratio between the daughter activity and the parent activity is constant over the time, and in addition to apparent decay rate, the daughter is controlled by the half-life of the parent. So there are two kinds of there are actually two kinds of radioactive equilibrium. First, we have defined what is the radioactive equilibrium, and now we are just coming about the different kinds of radioactive equilibrium. One is known as secular equilibrium and one is known as transient. Now, if the daughter half-life is longer than the parent, there will be no equilibrium between. If the half-life is longer, always remember, if the daughter half-life is longer than the parent, there will be no equilibrium between them, like in the case of technetium 131 and technetium. Secular equilibrium is one in which the half-life of parent is much longer, more than 100 times than the daughter. Example, 226 radium, that is half-life is 1622 years. So generally it called be known as secular equilibrium. So you should be able to define what is secular equilibrium and what is transient equilibrium. And now, like 226 radium, it is half-life is 1622, decays to an 222 Rn, that is half-life 3.8 days, and it occurs usually after 5 to 6 half-life of a daughter activity of parent A1, which is equal to the activity of daughter A2. Okay. Now, daughter's apparent half-life is equal to that of parent. So A1 equal to A2, or it can be told as, if A1 is equal to A2, then lambda N1 equal to lambda 2 N2. Okay. So A1, we are replacing A1 mathematically as lambda 1 N1, and A2 equal to lambda 2 N2. Now, if we plot a graph, the graph I will be showing you later. If we plot a graph against number of half-lives and the radioisotope activity, the radioactive equilibrium secular, that is, if we see the secular equilibrium, so now the daughter that is lambda 1 N1, lambda 2 N2. Now, lambda 1, lambda 2 are decay constant of the parent and daughter respectively. Here it is changing. Here the A1 is changing to lambda 1 N1. So lambda 1 and lambda 2 are decay constant of the parent and daughter, and this type of equilibrium is important in nature. Over a billion years, parent of the nucleum, uranium-238 or uranium-235 or thorium-232, have attained the radioactive equilibrium with their daughters. For example, radium is kept in sealed container. After a month time, all the daughters are in the secular equilibrium with the parent. So there is if we see that plot a graph that I was discussing, that if you plot a graph against the number of half-lives and the radioisotope activity, we will see that after a constant increase from like steep increase, there will be a time when it will go to a radioactive activity of 1 and it will not increase up then thereafter. So it is known as the secular equilibrium. Now we are coming to the transient equilibrium. We have just defined what is transient equilibrium. So transient equilibrium, half-life parent is no longer not much longer than half-life of the daughter, that is 99, for example 99 MO, that is half-life 67 hours, decays to 99 mm TC techtium, that is half-life 6 hours. After 23 hours of the 99 mm techtium activity, the production decay rate of the parent and daughter is equal. So 99 mm TC is said to be transient equilibrium with parent. And at equilibrium, daughter activity exceeds by about 10%. Later, the 99 techtium activity decreases so that apparent half-life is equal to the parent. Here, the ratio of the activity of the daughter to parent is constant and is given by the relation A1 by A2 equal to T1 divided by T1 minus T2. So, where here the mathematically T1 and T2 are half-life of parent and daughter respectively, and about 88% of MO decays into the 99 techtium through 99 M techtium TC, whereas decays into the 99 techtium without metastable state in about 12%, and in equilibrium 99 techtium activity is only 97%. The elution activity of 99 M techtium is about 90%, combining both decay and elution activity, and the overall yield is about 85%. So this is actually the radioactive equilibrium which I was discussing, and the different types of radioactive equilibrium and how they are mathematically plotted, that is how A1 is equal to A2 or lambda 1 N1 equal to lambda 2 N2, where you have to plot a graph and you have to also show what is the graph of a secular equilibrium and what is the graph of a transient equilibrium. Transient equilibrium graph just crosses this I will show you. Here is also same, but it is equal. So it crosses the parent and goes above, but it becomes constant after some time. So if we plot a number of half-lives against x-axis and radioactive activity against y-axis, we get a graph something like the equilibrium state. So this is known as the transient equilibrium and radioactive equilibrium. Transient equilibrium and secular equilibrium. Now we are coming to the nuclear transformation. Now nuclear transformation, when we mean nuclear transformation, it is generally meant by alpha decay. So radioactive nuclides with the high atomic number, like for example, if we have discussed already, that is when the Z is more than 150, mostly with spontaneous emission of alpha particle followed by the gamma rays and characteristic X-rays. After alpha decay, atomic number is reduced by 2 and mass number is reduced by 4. A typical example of alpha decay transformation of radium to radon or radium-226 has two decay modes. The first one accounts 6% and decays to excited states of radon with alpha energy 4.59 MeV, and the second decay accounts for 94%, directly reaches ground state of radon with alpha energy 4.78 MeV. And excited radon goes round state with the emission of gamma photons of energy 0.18 MeV. So if you see in the graphically, you will know, and the equation which we derive from that is like 88 Ra 26, which gives 86 to 222 plus helium 2 to 4 plus 6.4 MeV. This is actually the equation which you should remember, like when alpha decay transformation takes place of radium to radon and radon to radium to radon, and how the radium it is decayed and how the energy is produced. So, and whereas 6.4 is the transition energy released in the process, and the alpha particle is doubly ionized helium atom with a positive charge and about 4 times heavier than photons. Now you can see by the definition that how the energy is produced, and they are emitted from the nucleus with the discrete energies of 2 to 10 MeV, and the daughter radon is also radioactive and performs further alpha emissions, and after 9 transformation it's become a stable nuclei of lead 206. So this is the one of the example of alpha decay. Now properties of the alpha decays are like alpha particles are positive. Always remember, alpha particles are positively charged and causes intense ionization in matter, and the electric and magnetic field magnetic field of the, influence alpha particles is very important, and they have much shorter range and get attenuated with a few micrometer in tissue and 1 centimeter per MeV in air. Okay, this is very important. And the sheet of paper can cut off entire alpha particle, hence it is not used in medicine. However, research is going on to explore the therapeutic application, and alpha is high LET radiation and gives localized intense radiation in the living organism. So alpha particles are not generally used in the nuclear medicine purposes, but the research is going on. Now we are coming quickly to the beta decay. Now the process of radioactive decay in which the electron or negatron or positron is ejected is known as beta decay. Now here you should remember that when there is a electron or positron is ejected, electron emission is denoted by the mathematical sentence for the beta decay is beta to the power minus, and positron emission is denoted by the beta plus. Neither electron nor positron exists inside the nucleus, but it is created during the radioactive decay. Now beta minus decay, now nuclei having excess, now again here some of the mathematical expression you have to remember, that is nuclei having excess neutron performs beta minus decay to attain a nuclear stability, and in this transformation one neutron is converted into proton, beta and anti-neutron. Okay, and anti-neutrino, it is denoted by the V to the V, it is actually known as the V dash, and neutrino is a subatomic particle having neutral charge and mass lesser than electron, and antiparticle of neutrino is known as anti-neutrino. Hence the number of neutrons is reduced by 1 and the number of protons is increased by 1. So this is the actually beta minus decay. The like for example, if n is 0 to 1, which gives proton 1 1 plus beta decay minus 1 to 0, that is beta decay plus the V dash, which is known as anti-neutrino, and plus it gives energy. Now beta minus decay decreases the NP ratio and bring the daughter nearer to the stability, and beta energy is the poly energy spectrum consisting of the discrete maximum energy and the low energy. So the mean energy is equal to the E3 max by 3, and the remaining energy is shared by the neutrino, and beta particle is identical to an electron having same mass and charge. Always remember this difference between, you have known the difference between the alpha particles, the beta particles, the alpha decay their property, and the beta decay their property. Okay, so when beta particle is emitted, resulting a new atom has same number, but an atomic increases by 1. Beta particle carry the entire charge released by the energy. A typical, now we are coming to the example. For example, beta decay transformation of cobalt to nickel. Okay, cobalt is CO and the nickel is Ni, as shown in I will share it in later. First let me explain it to you. Like the cobalt 60 decays to excited state of nickel 60 with beta kinetic energy of 0.313 and 1.48 MeV respectively, and excited nickel 60 goes to ground state with the emission of gamma rays energy of 1.17 and 1.33 MeV respectively. So if cobalt 27 by 60, it gives nickel 28 by 60 plus beta decay minus 1 to 0 plus V dash, which is known as the anti-neutrino. So anti-neutrino also occurs in the alpha decay, and anti-neutrino also occurs in the beta decay. Now what are the properties of beta decay that you must know? Beta decay, as it is very clear, it is negatively charged and it can cause ionization in the medium, and they are deflected by electric and magnetic fields, and the range of the beta particle is higher than that of alpha and get absorbed by the few mm of thickness in aluminum. They perform localized biological effect on the living tissue. Okay, now we have discussed about the beta plus decay. Now we will discuss about the beta minus decay. Now we will discuss about the beta plus decay. Now nuclei having lesser neutron, when there is a plus here, when the beta plus decay is going on, then there is a nucleus which is having nuclei which is lesser neutron number performs beta plus decay to attain the nuclear stability, and in this always transformation, remember, one proton is converted into neutron, beta plus neutrino V. Okay, so here the number of neutrons is increased by 1 and number of protons is decreased by 1. So you have to remember this: if proton 1 by 1, which gives 1 by 0 plus beta decay plus 1 to 0, which is known as beta decay, plus neutrino V and plus energy. Now the daughter will have more electrons initially, referred to as negative ion, and later it will emit excess electrons in the orbit and become neutral. Okay. So when the beta particle is emitted, resulting in the new atom has the same number, but atomic number is decreased by 1, and beta plus particle is positively charged and named as positron. It is an antiparticle of an electron having same mass but opposite charge. So positrons are polyenergetic like beta particle, and mean energy is equal to E max by 3, and positron decay has threshold. The parent should have excess mass than the daughter, which is equal to the mass of 2 electrons. So radioisotopes that are produced by an accelerator is neutral, deficient, and they decay with the positron by increasing the NP ratio. Like for example, if nitrogen, if the nitrogen is 13 and nitrogen 13 decays directly to the ground state of carbon 13 with positive positron energy of 1.19 MeV and no gamma is emitted, so it will be like N7 by 13, which gives C6 by 13 plus positive decay and plus V, and V is antineutrino. The mass difference between the parent and daughter nuclide should be at least equal to 1.002 MeV for positron decay to happen. The positron does ionization and excitation in their path come to rest. Now they react violently with the electron to their entire mass, and that is converted into 2 gamma photons. Now that is very important, 2 gamma photons of energy 0.511 MeV, and this process is known as the positron annihilation, in which 2 photons are emitted at the 180 degree apart to conserve momentum. Now this is a typical example of Einstein mass energy equivalence, where E is equal to mc square, where m is the mass of the particle, c is the velocity of the light, and this is the principle used in the positron emission tomography. This same principle is applicable when we do a PET scan. So here the E is equal to mc square, where the Einstein, the mass energy of relativity theory is applied, and positron decay in light, proton reach a nucleus in which the parent-daughter transition is equal to more than 1.02 MeV. Now we are coming to the electron capture. Now what is electron capture? Electron capture, now for example, we will be discussing about nuclei deficient of the neutrons may undergo decay by absorbing its own K or L shell in the electron, because we have discussed already the different atoms, the K shell, L cell, M cell, etc. So nuclear deficient of neutrons may undergo decay by absorbing its own K or L shell electron, and when an electron is absorbed, it combines with the proton and is converted with the neutron with the emission of neutrino. Okay, that was when the V is dash, it is anti-neutrino, and this is known as neutrino. So one proton, 1 by 1 proton plus if electron to the power minus 1, it gives neutron 1 to 1 by 0 plus neutrino. The electron capture is like that of positron decay, and the atomic number decreases by 1 and the mass number remains constant, thereby increasing the NP ratio. Now example like chromium 51, now it decays to vanadium 51 through an electron capture process with emission of gamma rays of an energy 0.32 MeV. Okay, that is if the chromium 5124 plus energy, it gives 51 by 23 V plus neutrino plus energy. So this I will be giving you in the PDF format by a diagram explaining, but you have to know what is electron capture, what is beta plus decay, and that you have to define. Like they can ask you what is beta minus decay, and what are the stable, what is the radioactive equilibrium, what are the nuclear transformation. The nuclear transformation, you have to always remember the alpha decay, beta decay, gamma decay, what energies are liberated, and what is the formula for the Einstein. That's E is equal to mc square, and where beta minus decay is taking place, and where beta plus decay is taking place, and what is beta plus decay, and what is electron capture, and how electron capture radioactive decay by the electron capture process, how it is processed. Now this process I will be sharing you with a diagram, which I will be in my next video, which is part 3, because I am going with the radioactivity and gamma rays only in the radiology now for the PGTs. So I will continue this, because this chapter is very conceptual, and the many questions are sometimes their questions are asked, because I have seen 2-3 years ago question which has been asked in the various universities. So it is more likely that this question, like asking of radioactive equilibrium and the beta plus or beta minus decay, or the equations or the diagram of beta plus decay or radioactive decay, so these are electron capture may be asked, and you should be able to give the answer confidently. Now, okay, now I am after electron capture. I have just told you about electron capture, and the next I will be starting with internal conversion, gamma emission, and then the nuclear reaction. The nuclear reaction is in the form of like alpha alpha bombardment, which is done by the Rutherford, and proton and deuteron bombardment, neutron bombardment. So fission, fusion, chain reaction, the production of radioisotopes, okay, the nuclear reactor, etc. This I will be completing in the next part. Cyclotron. These are very important thing, and this very important concept, and this equation you have to always remember, and this can be asked as always as a long answer question. So you have to remember this. And yes, so I am just concluding here with electron capture only, and just whatever I said about electron capture, how electron capture occurs, and what is the example, how the electron capture it decays, and with the emission of gamma rays, and to the energy of how much MeV, that you have to remember. And the diagram which I will be giving you in the next very class, which I will be taking within 2-3 days, I will be giving you the entire diagram of beta minus decay scheme, like for example of cobalt 60 radioisotope, which I have just talked, with beta plus decay nitrogen 13 radioisotope, with electron capture of radioactive decay of the electron capture process, then about the beta spectrum of 32p suggesting to polychromatic nature. This I will be discussing with the decay scheme of radioactive radium 226, radioactive equilibrium, and already which I have discussed about the worked example of how to calculate the remaining activity and etc. I will be again discussing, and I will be giving you by a PDF, in which the PDF you will just remember, and then you can learn it from there. So from the in the next chapter I will be giving you the diagrams, the various diagrams which I have just told you as a theory, and then we will move ahead with the electron capture only, because electron capture I have completed. Electron capture, the various shells I have not yet completed. Let me first give you the diagram, and then I will be able to complete the entire chapter. And then after the radioactivity and the gamma rays, we can go directly to the production of X-rays, because this is very important. The production of X-rays is highly important. Many questions comes. Radioactivity and gamma rays questions are not so much important in the radiology. It is actually important in radiotherapy. Nevertheless, the question always comes. So I cannot predict that which question will come or which question will not come. But the thing is that you have to remember the entire concept and entire diagram. So that I will giving in the next class. Thank you.